Happy to introduce Foteini, who's an associate professor at Mysten and also a research advisor to Mysten Labs. She does a lot of really cool live cryptography and work on blockchains in general. Her talk is not about snarks, despite being very snarky, but the techniques are related, and I'm excited to hear about it.
Thank you so much, Justin, and thank you for having me here. So I'm very excited to talk about a very recent work that is going to appear in crypto in a couple of months. This is a work on decentralized storage, increasing scalability of proof-of-replication. And it is joint work with colleagues at George Mason University and also Mysten Labs. Well, Matteo used to be at Filecoin when we started this work, but now has moved. Let me start with a brief introduction on some of the fundamentals in the space. And let me first introduce what we mean by the notion proof of space. So in a very abstract way, you can think a proof of space as an interactive protocol between a prover and a verifier. So you might have a prover that has committed to dedicate a certain amount of storage, so let's say 1 gigabyte, and it wants to convince the verifier that indeed it is using this space. Proofs of space have been proposed as an eco-friendly alternative to proof of work. And they have found applications on Sybil-resistant blockchain consensus, but also spam protection, DDoS attack resistance, and so on. An important note to make about proofs of space is that the statement that the prover is proving is literally just the fact that they are committing a certain amount of space, but in the typical proof of space setting, the prover does not prove anything about what are the data that they are storing. Okay, so the data, it's not particularly helpful or specific. It doesn't really matter what the data is. Proof of replication is related to proof of space, but tries to solve this exact point that I made before. The prover receives a particular piece of data, and they commit that they dedicate certain memory to store that exact data D. Okay? So I like to separate the phases, the process of a proof of replication by 2 stages, the setup phase and the audit phase. So in the audit phase, the verifier again is going to challenge the prover, and the goal of the prover is to convince the verifier that indeed they have committed that much space, but also that they are storing this particular piece of data. The reason that we care about proof of replication as opposed to just proof of space is that you don't waste the space of the prover. You can actually use the space to prove something useful. And in a very abstract level, the security guarantee that you want here is that the prover is going to dedicate unique storage resources for every replica of the data. So proof of replication can be very useful to build decentralized and verifiable file storage. An important also point that I want to make about both proof of space and proof of replication, I mean, these are proof systems. You would typically think that their basic security requirements would be correctness and soundness. But there is one more property that is relevant and very important in both settings here, and this is the notion of space gap. And again, in a very high level, and we're going to formalize this a little bit more later in the talk, when we refer to a space gap, or sometimes also called the tightness of a proof, we refer to the difference between the amount of space that the prover claims to have dedicated here and the actual space that they're using in order to compute their proofs. Okay, so obviously, the tighter the proof here is, the more secure the system is. Another way to think about proof of replication is as a combination of various other types of proofs that have been proposed in the literature. So you can think of it as proof of storage. Again, the prover is proving that is dedicating a certain amount of space. Proof of data possession, that the prover is really holding that particular data that you asked him to prove. And also proof of retrievability, in the sense that the prover should be able to return back this data if it is asked to. Proof of replication has found applications, as I said before, in various settings, but the most prominent one, and the one that we, this crowd here, I would guess, cares most about, is Filecoin. I assume most of you are familiar with the basic idea of Filecoin. It is an open source cryptocurrency that at the same time also serves as a decentralized storage system. Users are willing to pay some amount in order for their files to be stored. And of course, we want to do that in a way that users can be sure that their files are retrievable and they can get them back. So if we try to think a little bit about how Filecoin works, as I said before, we have users. They are willing to pay a fee in order to have some providers that are participants in the Filecoin consensus protocol to store their data. The storage providers will guarantee through the blockchain that they are indeed storing the data, and there are also these retrieval providers that help users to retrieve their data back. But the important phase here is the phase of Filecoin verification, because, as I said, it is very, very important to make sure that indeed whoever is the prover here, indeed whoever is storing the data, they actually have the data at any time. So proof-of-replication comes exactly at this point, and it has to guarantee that data is stored and readily available to be retrieved. Okay? And our focus in this talk is in this part of Filecoin verification. In systems like Filecoin, where you would imagine that you would have a very large number of participants, there are certain properties, there are certain efficiency requirements that one needs in order for the system to work practically. The first one is what we call laconic challenges. So remember that I said before that there is this sort of auditing phase that we want to make sure that the server is storing the data. And as I was showing you before in this interactive protocol, there is some sort of challenge that comes from a user to the prover. So ideally, we want these challenges to be very, very short, and ideally of constant size. The second property that we aim for is to have both the prover and the verifier to run in time sublinear to the number of files that are being stored. And finally, we also want to have a robust space gap. And remember, the space gap is the tightness of the proof that I mentioned before. And ideally, we want to have like an as secure protocol as possible. So these are the three parameters, the three requirements that we are trying to optimize when we're building large-scale proofs of retrievability. So there has been a lot of work in all these types of different proofs, proof of space, and so on. I'm not listing all these works. You can refer to our paper. There are like dozens of them. But I want to refer a little bit to this work on proof of replication by Ben Fitz from 2018, which is the one that is the most relevant to our work. And it is the one that we're kind of comparing directly. The idea here is this setup phase. The verifier, the user, they're going to send data to the prover. And the prover is going to perform some pre-processing on this data and commit to them. In this particular work of Fitz 18 and of many other previous works on proof of replication, what happens is that the prover is going to build some sort of graph structure over the data that they are building, that they are storing. And they're going to, we call this the encoding phase, where they're going to encode the files, the data, through a graph structure. And the goal would be to do it in a way so that they can later convince the verifier that they are holding the data and they have also like dedicated a certain amount of memory. So in the audit phase of such protocols, the important part to notice is that the verifier is going to challenge the prover on a subset of the nodes of the graph. So the challenge here, it's not a single challenge, but it is a challenge that consists of many little pieces. And the prover will return back proofs. The tightness of the proof here, it will really depend on how large the challenge is. Okay? So the more challenges you give to the prover, the higher are the chances that the prover is not sitting here. So the auditing phase, as I just said, it is probabilistic, and a large set of challenges is going to be needed for a good level of security. So what we're trying to do in this work is to come up with a proof of replication protocol that will have this auditing phase that will allow the verifier to send a single challenge. And with a single challenge, we want to make sure, in a deterministic way, that the prover is holding all the data. Okay, so we're trying to get from like multiple challenges to a single challenge, and at the same time get like a very high level of security. So as opposed to using these special types of graphs, our technique is going to be based on polynomial evaluation. All right, so let's see how we do it. And I'm going to start with getting a little bit more formal and defining first how we describe proof of replication. We define proof of replication as a set of 5 algorithms. So first, we have a setup algorithm. It takes as input different parameters that they're going to become apparent a little bit later. They have to do with the time of the prover and the memory that the prover uses. This setup algorithm is going to output 3 public keys, an encoding key, a public key, and a verification key. And notice here that there are no secret keys, so the scheme is completely trapdoorless. Then there is this algorithm that we call the encode algorithm that will take as input the message or the data. It will take the encoding key and some identifier ID. You can think of it as being some sort of a salt. Okay, and the reason that you want that is to be able to have different encodings even if you encode the same piece of data. So this encoding algorithm will output an encoding and some digest aids, and this digest aids is going to be published. So this is the pre-processing phase. And then we have the audit phase. And in the audit phase, we essentially need a proof algorithm that using the encoding and the proving public key and a challenge, it will output a proof. Together with the proof algorithm will also come a verification algorithm, which having as input the verification key, the public digest aids, and the proof will output accept or reject. Finally, we also have a decode algorithm that using the encoding and the encoding key, the encoding C and the encoding key, it can return back the original message. Okay, you can think of this as some sort of like decryption algorithm. So the security properties that we want here are going to be encoding correctness, proof completeness, and also replication and extraction. And I'm going to focus on replication and extraction because these are the kind of more non-standard properties here. Remember that the goal of our work is going to be to reduce the complexity of this phase, right? So remember what I said before about how we compare with the work by Ben phase. We are trying to make sure that when you're proving, when you're being audited, you can just do it with a single challenge for the full set of data. So let me start by defining replication, which is, I think, the most interesting property. Informally, the replication property should guarantee that the amount of memory that the prover is using has to be specific in order to be able to produce proofs that verify. So let me explain that more formally. So we're going to define this by a security game and assume that we have a challenger that first runs the setup algorithm. And then we give all the public keys to an adversary, and the adversary is going to select a set of messages. Okay, so this is the messages, the data that you want to encode. Then we're going to run the encode algorithm, and notice here that the encode algorithm is run honestly, and I'll keep that in your mind, and I'll get back to it soon. In order to run the encode algorithm, we are going to pick these random identifiers, and again, recall that these identifiers, they can just be viewed as some sort of salt here. And we are going to encode, the challenger is going to encode all the messages that the adversary selected and output the encodings and the digest for each one of them. Then all these encodings and digests, along with the IDs, are going to be given to the adversary. And the adversary is going to output some value alpha. That is basically the adversarial memory that the adversary is trying to create here. We're going to sample a challenge from the challenge space. Recall again that we have a single challenge here. And we're going to give now the challenge to the adversary. And the goal for this adversary, by only having access now to this special value alpha that created in the previous step, would be to output a bunch of proofs that are going to be accepted. All of them are going to be verifying. And we are going to say that this adversary breaks replication of the system, wins this game, if it manages to produce such accepting proofs while using some piece of information, this alpha, the size of which is less than n, where again, remember that n is the amount of memory that you would need in order to store all these files M1 to MU. Something to also mention here is that in certain settings, the messages that you're trying to encode in these systems might be messages that are naturally very easy to compress. think, for example, that you might have to store a sequence of messages that are basically evaluations of a PRF on some counter or something like this, right? In that case, you could have a prover that basically avoids to store the data and just generates the data on the fly when they're asked to create a proof. That's the reason that for this kind of protocols, we are going to need an encode algorithm that is going to be slow, okay? That has to be forced to be slow. And at the same time, it has to be the case that the running time of the adversary that creates the proofs is less than the time that this encode algorithm runs, okay? Because again, otherwise, you could have the adversary running the encoding all over again, okay? And we're going to see how we guarantee this.
So question, so why is it bad if you had someone storing a compressed version, if it was highly compressible data, like as long as a user can retrieve it?
So exactly because these proofs of replication, they want to combine the property of proof of space as well. You want to maintain the property that you are dedicating a certain amount of space.
Right, but I guess my question is why? Right, if I can get the data, why do I? I mean, I definitely get the fact you don't want to just like pass through the query to someone else.
Right.
So I get the idea that you want decentralization, you want replicated storage. But like if I had like 10,000 people all storing it locally compressed.
I think, Joe, you have a good answer on that?
So, Tim, I think compressibility can vary from person to person. So there's an attack on these schemes where you upload some giant file that you know the PRF key that generated it. So you can store it very succinctly, but everybody else can't.
And then?
Well, then you're sort of like possibly making other people store more data than you are.
So I'm just trying to, so like, you're just thinking about some malicious user who...
That was like the original concern, I think, when we were looking at this like years ago. It's just that like you would have some secret compression key that would sort of like let you compress the data, but not anybody else. And then you could sort of get credit for what seems like you're storing a lot of data.
So the way that I think about it is that because they're using this in this like proof of space-based consensus algorithms, they do want to make sure that validators are dedicating a certain amount of storage. And between different validators, maybe some of them are getting files that are compressible and some others are getting files that they're not compressible, but they want to make sure that all the validators are saving the same amount of space. So they really want to enforce that this is what is being stored.
So it's really important, I mean, so this is really optimized for like civil resistance and consensus,
Yes.
as opposed to just like data availability of
Correct.
roll-up data or
Correct.
something like
Yeah.
that.
Yeah. So we should be thinking of this as really, like how to improve Filecoin potentially.
Okay.
Yeah.
Okay.
Another point here, and this is something that it's different from the work of FIS, is that if you notice our security game, you're going to see that we don't let the adversary run the encode algorithm. We actually run the encode algorithm honestly. This is different from FIS 18 because there they actually assume a malicious encode. However, just to make Justin happy as well, this could be resolved by adding a snark along with the output of the encode to make sure that the encode was run correctly. But nevertheless, the focus of our work is not to improve the encoding phase, but to improve the audit phase. Okay, so even if this requires a snark at the time of encoding, we don't consider this a problem. We are fine with having a more costly pre-processing phase because we're really trying to optimize the audit phase. But definitionally, this is a difference from prior definitions. So remember that before I also said that memory, the memory gap is important in these proofs. And again, we define the memory gap as the distance between the space that you would need to store all the files, all the messages, and the replication parameter n, so this memory that you would have to hold here. The smaller the gap, the better is the robustness of the proof-of-replication system. Okay, so basically, if an adversary wants to pass the verification with non-negligible probability, then it will be forced to spend memory, to dedicate memory that is very, very close to the actual memory that it would take to store all these files, actually. Yeah. So the second property that I'm going to define is that of extraction. It's not a very fancy property. It's the typical extraction property that you would see in such proofs. And it basically says that all messages are going to be retrievable when a prover who holds the encodings produces valid proofs. So again, we define this through a security game. We have a setup algorithm, outputs all the keys. We have an adversary that is going to select the files. We are going to run the encode algorithm exactly as before. We're going to give the digest and the encodings of all the files to the adversary. The adversary is going to try to compress them or like put them in some sort of data structure alpha. And now we define the existence of an extractor that will have Oracle access to this A3 that is producing the proofs. And what we want to make sure is that such an extractor exists. And if it manages to get valid proofs from this adversary A3 by only providing challenges to this adversary, then the extractor will be able to extract the messages that were encoded in the encodings. Okay, so these messages should be the same as the original ones. So the extractability property is, more of a needed property for like the proofs of this instance. So let's talk a little bit about our construction. And let me start by quickly going over some of the basic building blocks that we use here. And the first building block that we utilize is that of memory hard functions. Again, in a very high level, you can think of a memory hard function as a deterministic function that takes an input and evaluates it, an input x, and evaluates it into an output y. And the special thing about these functions is that these functions take a long time to run. Even if you try to parallelize the process, they do require a certain amount of memory to be dedicated in order to evaluate them. There have been multiple proposals of constructions of memory hard functions. And again, the security property here is what we call input-dependent and potentially multi-instance as well pre-processing. So multiple input evaluations are completely independent, and pre-processing does not really help. Okay, so it doesn't matter if you have done any sort of like pre-processing here. Whenever you have to evaluate a new input, that should be completely independent from anything else that you did in the past. The second building block that we're going to use here is that of polynomial evaluation. And the observation here for our construction is that basically what we're going to do is to encode the files, the messages that we want to store, in the form of a polynomial. Okay? So I'm going to define a polynomial f of degree d that is going to be sampled randomly from a field z of order p. The idea is going to be, like when we're talking about polynomial evaluation, the idea is that the verifier is going to be sending some inputs to the prover, and the prover is going to be evaluating the polynomial in these inputs. Remember, though, that an important property here is that we want to make sure that the server is really dedicating a certain amount of memory here. So it is important to understand how much memory, if we assume that there is a way, and I haven't shown you how yet, if we assume that there is a way to represent the data as a polynomial, we have to make sure that the server is really dedicating the right amount of space here, the right amount of memory to store. The observation here is that there is this result about incompressibility of random polynomials. So again, assuming that we have a polynomial that is randomly sampled, the property that we want here is that in order to evaluate this polynomial, you should require memory close to the size of the polynomial. If you have an adversary that tries to pre-process the polynomial and compute a memory alpha, this data structure alpha that is smaller to the size of the polynomial, it shouldn't be able for this adversary to evaluate this polynomial on random points. Okay, just by using this alpha data structure, unless, again, this data structure is of size similar to the polynomial. So also, I'm going to denote the size of the polynomial as the degree of the polynomial times p, where p, again, was the order of the field. So luckily, we have a result, an existing result on this by Yatenyeze et al. From PKC 23, which basically says that for random polynomials, it shows that the amount of memory that you would need in order to be able to evaluate the polynomial in random points is actually pretty close to f of x. It is actually d times p minus d times the size of q, where q is the subset from which the evaluation points are being sampled.
How do you prove this result?
It's a completely different work, and I'm happy to talk to you about it offline, but it's like an existing result. It's not something that we did in this work.
And is this prior work also in the same context or different context?
It's not about proofs of retrievability. It's literally about incompressibility of random polynomials. So just to give you one more hint about how this works, basically they reduce this result to incompressibility of random strings using some Kolmogorov analysis. But again, we're using this as a fact. We have to do, the only difference in our work is that we had to do like a small tweak just for the parameters, but it's not a new result. So again, the observation here is that what I want you to keep is that as long as these polynomials that we're going to use to represent our files are random, they're not going to be compressible. So let's get now a little bit more specific on how the encoding phase is going to work for our system. And again, remember that this encoding algorithm is going to take as input the messages, the files that you want to encode, a key, and this random identifier, and is going to produce an encoding and a digest. For now, let's just assume that we're trying to encode a single file, a single message M. And let me take this message M and break it into smaller blocks. And I'm breaking my message into D blocks. Okay, and the size of every message is of size P, where again, remember P is the order of the field from which you sample the polynomial. What we're going to do is that we're going to combine this random identifier along with the message in order to derive the polynomial that will appear like it was randomly sampled from ZP. So first, we're going to use the memory hard function, and we're going to run it over the random IDs, which, as I said before, we can use them, we can sample them from a random beacon. Okay? So this is going to give us this first value v. And then we are going to compute the polynomial by hashing this value v with the ID, where h, you can assume that is a random oracle. And you're going to XOR this with every block of the message. So in a sense, you can think that every block of the message is going to be roughly a coefficient of the polynomial. Okay? So a note here about h, about the random oracle. The reason that we model this as a random oracle is because it allows our construction to be a little bit more modular. It doesn't require any specifics from the underlying memory hard function. But if you open up the box here a little bit, you might be able to avoid the use for a random oracle as long as the memory hard function has certain properties. Okay, but it's much easier to think about it in a more modular way, assuming that this is a random oracle here.
What's the point of the memory hard function? I think I'm lost on that.
Great. So the point of the memory hard function here is to ensure that the encoding is slow.
But I mean, memory hard is not slow, right? It's memory hard. Like it might be fast if you have.
Well, by slow here, I guess dedicating certain memory.
I see.
But why would you want that in your encoding process?
So this is going to become a little bit more apparent as we look into more details. Trying to see what's the easy answer I can give. Sorry, I'm getting.
You get like your memory usage is at least depth robustness of the memory hard thing plus like degree, right? Something like that.
I'm sorry, I didn't.
Sorry, like you're like you have the gap between the amount of memory you need and the amount of memory you want to store them with depth robustness of the memory hard function or whatever, right? Underlying or whatever,
Right.
you have like
Right.
that's like some minimum guarantee plus like the degree because you have this result like you need at least d minus this, and
Right.
so you want it to be at least some threshold. And you
Right.
Yeah.
So-
Okay.
Right.
If you want it to be slow, why isn't it a VDF instead of a memory hard function? It seems like that's the specific thing for slow.
Would the VDF also have specific requirements on the memory side?
No. But I guess maybe I'm confused. Like, does the memory requirement here come from the memory hard function or from storing all these kind of like random?
From like the proof of space part.
Yeah.
So I don't know. I would have to think about replacing this with a VDF.
It seems like you need memory to store the polynomial, right?
Right.
So.
And you cannot compress that.
Yeah. And then if you want slow, like a VDF, that's its whole job is to be slow. Whereas the memory hard is like, it's sort of slow, but that's just like a byproduct of what it's really trying to do.
Yeah, that's a fair point. I can think about it. Yeah. back to the encoding. This is basically how we represent the messages as a polynomial. And that's the output of the encoding. We're not done yet, but let's try to see how things are standing right now. So we have the server that received all this data. I'm not showing that in the picture. And in this pre-processing phase, the server is going to prepare one polynomial per message. So here in the previous slide, I was just showing the process for a single message, but now assume that you're doing that for multiple messages. Okay, so you have a different polynomial for each message. And now our goal will be to design an audit phase where the verifier will send a single challenge, a single random point, and the prover will evaluate all these different polynomials on the same random point. Okay, so this is what is going to give us a single challenge as opposed to having multiple challenges here. So what have we done so far? So we can get a single challenge from the verifier and still getting all these evaluations on all these different polynomials, be sure that the prover is storing all the data. And we have also enforced the use of space by making sure that the polynomials are not compressible. What we haven't done yet is we haven't achieved sublinear proving time. We haven't explained how proof is going to work. And also, we haven't talked at all about how the verifier is going to verify that indeed the evaluations that it receives are correct. Okay, so let's try to answer those two questions as well. So let's get first into the sublinear proving time. There have been multiple works that focus on how to speed up the evaluation of polynomials. But the one that we're actually going to use here is a very cute result that it's like more than 10 years old by Kedlia and Uma on fast polynomial factorization and modular composition. So the nice thing about this work is that it uses a RAM data structure in order to expedite polynomial evaluations. And by doing that, it does achieve the evaluation of the polynomial to happen in polylogarithmic time in the degree of the polynomial D. So the way, again, I'm not going to get into too many details because this is like not work that we have done here. But it has two algorithms. It has this algorithm that generates this data structure that gets as input the polynomial and creates this data structure D, and then evaluates the polynomial in random points, a random point x, by just using this data structure. So again, a very, very high level, it is going to leverage RAM access to this data structure D in order to only access the blocks from D that are going to be relevant to evaluate the polynomial. It does come with a caveat, though. And I want to convince you that this caveat is not a big problem for us. Okay? So the caveat in this work is that the size of this data structure D that it requires in order to then speed up the evaluation of the polynomial basically expands the size that the polynomial has. Okay? So it has this like memory expansion problem. It actually expands and enlarges the memory by a factor gamma on top of the size of the polynomial. Okay? So the trade-off here is that we're going to get faster evaluation with a single challenge, but our provers will have to dedicate more memory. So this gamma can be defined in terms of the degree of the polynomial and the order p, and some constant factor delta. So the smaller this constant factor delta is here, the smaller is going to be this data structure, the slower is going to be the evaluation. And what it was shown in this prior work is that any delta that is greater than 1 is actually going to be sufficient to achieve polylog evaluation. I should also highlight at this point that trying to come up with concretes for this work, it's going to look pretty ugly. So the main contribution of this work is mostly of theoretical interest. So the advantages are going to be on an asymptotic level. Okay, so playing with constants here, it's not easy. All right, so having that result, we can...
So intuitively,
yes.
Is that just saying it's like a way to store the polynomial redundantly to speed up evaluation beyond the average?
Exactly. And then access only certain parts of the memory in order to evaluate it. And that's why you can get evaluation in polylogarithmic time.
And are they coming more from like a complexity theory motivation, or?
Yeah, it's not easy to explain, actually.
Okay.
Yeah.
That's still like Uman and not Umans. It really feels like a Chris Umans result, you know what I mean? But, Okay.
So it's a result that I didn't know about. I don't know how, I have a feeling that it's a result that it's not being heavily used in,
Because it's
very
It's-
theoretical.
It's very complicated.
It's very complicated too.
it's a lot of Chinese remaindering.
Yeah.
Right. Like, but also, like, it's not clear to me. If you ask me about, we had this discussion on the rebuttal of the paper. If you ask me about the concretes of this work, it would be very hard to answer.
It is the kind of thing where it's not even clear that in principle you should be able to do that, right? So
Yeah, that's right.
it seems kind of cool, even just in principle.
Right. But again, like in this setting where you don't really try to optimize this pre-processing phase and how much memory you really actually want the users to be storing lots of memory, it's not a big deal.
You could also just store the whole table of field evaluations, right?
But
It's too big,
Yes,
but it's
sure.
too big,
Yes.
but
we're gonna, but then, as I'm gonna say in a couple of slides, this will also help to get a polylog verification time. And if you store the whole table, this might be a little bit. Utilizing this result can also give us sublinear proving time. So the last thing to resolve here is how can we also run verification in sublinear time, and we also want to do that in polylogarithmic time. So the observation here, the first attempt that again would make Justin happy would be to let's assume that we're just going to use snarks. So whenever the prover evaluates the polynomial, using this special data structure, it can also attach a proof and say, hey, that's why the evaluation is correct. But again, the problem here is that the prover time will become linear to d. Okay, to the size of d, and that's something that we don't want here. Again, we want to have a sublinear verification. We're trying so hard to have sublinear proving time, so now we're gonna increase that again. Our trick here was to basically have the verifier also evaluate the polynomial locally in the same way that the prover is gonna do it. Okay, so how do we do that? Of course, the verifier does not have access to this whole data structure D, and we don't want it to have access. But remember that we said that in order for the prover to evaluate the polynomial, it will only need to perform RAM access to particular blocks of this data structure. Okay, so how about we just provide these blocks, which are going to be of polylogarithmic number, to the verifier. So the way that we're going to do that is by building a Merkle tree on top of these blocks of the data structure. And then when the prover evaluates the polynomial, it's going to give the evaluation. Again, I'm doing this for a single point, but for a single file, you could be doing that for multiple files. You're also going to send the digest, the root of the tree, the blocks, the subset of the blocks that you use for the evaluation, and the Merkle tree proves that they belong to the digest of the tree. Okay, and this part you can actually think of it as happening during the pre-processing phase. Okay, so now the verifier would just have to check proofs, the Merkle tree proofs, and then it would have to reevaluate the polynomial and check if the values that it got from the prover are the same ones that it locally computes. And this way you can also achieve polylogarithmic verification here.
How much memory was it to compute the polynomials? Because the verifier will have to have that much memory, right?
It's polylogarithmic to the size of d.
Or even the memory was small?
Which memory?
Or like you said that like the algorithm which runs in polylog time,
Yes.
the memory that it uses was larger, right?
Yes, d is so the memory that the prover needs is d. And d is slightly, it has an expansion factor over the size of the polynomial. So it's larger than the polynomial. So to recap how the scheme works, we do have this encoding or pre-processing phase first. We are going to prepare one polynomial per message, per file. This is going to be our encoding. Then using this special data, we're going to generate this special data structure for each one of the polynomials. We're going to build a Merkle tree on top of each one of them. And this is going to be our digest. Potentially, we're going to also give snarks here that things were well formed if we actually care about honest encoding, if we care about malicious encoding execution. We're going to publish the digest, potentially the proofs if we need them so. And then the nice thing about the audit phase is that we can do it with a single challenge. It's going to take polylogarithmic time on both the prover and the verifier side.
Quick question. Is DI, is it the evaluation of some related polynomials? Is it kind of evaluation?
With DI?
DI, yeah, the data
DI
structure.
is this special RAM-based data structure that you're going to compute. on top of the polynomial in order to be able to do the quick evaluation.
And if you use like something like polynomial commitments instead of Merkle trees here, do you think we can go around generic snarks and use something like targeted?
Yeah, you could potentially. The focus here was not so much on trying to optimize anything on the pre-processing phase. Basically, the trade-off that we're trying to solve is, we're willing to increase the amount of memory that the prover is devoting. We are willing to have a more expensive and a slower pre-processing time at the cost of having a verification, like an auditing phase that is more challenging. Because if you think about it, this whole pre-processing happens once. Yeah, but this like auditing phase happens all the time. So I think in Filecoin, if I'm not mistaken, it happens about like 10 times a day. So you audit these validators about 10 times a day. And you want to be able to audit in a way that the auditing is not really probabilistic here, right? So with a single challenge, you're just auditing the whole structure, the whole data structure of the whole memory of the prover.
I think one thing you can say about the polynomial commitment suggestion is the committer here is honest. It's the pre-processing. So this is like a really nice polynomial commitment scheme if the committer is honest. Probably
Right.
can't do better than this, would be my guess.
Right. Right, but if the committer was not honest, then you can start thinking about better ways to resolve this problem. And again, as a comparison, the work by Ben Fies, it assumes a malicious committer. And that's an important difference. All right, so let me conclude by giving you a comparison, an asymptotic comparison with the work by Ben Fies. So this is the work by Ben Fies, and this is our main construction. The main things that I want you to notice is that we're fixing these to be the same. So in a sense, you can think of those two columns as being the level of security offered by both schemes. And under the same level of security, the advantage of our scheme is that the number of challenges that you need is constant, as opposed to having challenges that depend. Here is the total number of files that are being stored. So you have a single challenge as opposed to something that depends on the number of files being stored. The runtime for the prover and the verifier is polylogarithmic on the degree of the polynomial, or else the number of blocks that every file contains, as opposed to u squared log d. And the caveat here, what we're paying here, is the fact that the memory expansion of the prover, the amount of data that the prover needs to store, is going to be quite large in our case. So again, it is a trade-off, and it really depends on how fast auditing you want to get here, and whether you want auditing to be like on the full set, or you're happy to just be auditing certain parts of the structure.
Do you ever think about, or did you compare to like a sort of a wrapped version of Ben's protocol where you still have like n challenges, but then you compress them all with some generic snark scheme?
We haven't compared. We haven't tried to do a comparison this way. It's not clear to me whether this asymptotically would be any better.
Well, I mean, you could keep the simpler setup and expansion of the fish scheme, but then you wouldn't have to actually post all the challenges and responses on chain. You could just sort of commit to them, which you could do quickly, and then even if it takes you a while, you could come up with a proof within some time that says that they're all correct. So you could get, I guess I'm just thinking like, at the time...
It's not clear to me that the proving and verification time would actually be polylog here if you do something like that.
Would be better?
I think it wouldn't be better if you try to do something like this.
I mean, it could be pretty fast if you did like Groth 16. You could prove that all the challenges are correct, potentially like very...
For like the full set?
Yeah,
it's not clear to me. I'm, again, happy to discuss this more.
I guess the reason I thought of it is that at the time Ben was designing that protocol, I think like, I mean, this idea of only having like one challenge or constant number of challenges wasn't wasn't something we thought about. It's pretty interesting, but I wonder if there's another way to get there.
Yeah, I'm happy to talk about it if you think there are better ways.
Well, just a different way. I don't know.
Yeah. I mean, I should also probably say that Filecoin uses something much simpler than all these. It just uses like Merkle trees and I think snarks now as well. But it's interesting because we started this project in collaboration with their team, and they seem to be very interested about how you could possibly do something like this, just with like a single challenge and have this kind of deterministic audit phase. But again, like trying to actually make like the parameters practical here, it's a nightmare. So it's mostly of like theoretical interest as a result.
Does things change if you do multivariate polynomials?
We are actually using multivariate polynomials.
Oh, so okay.
I mean, I'm putting multiple things under the carpet,
Gotcha.
but we are, yeah.
And are the security proofs, are they straightforward? Or
They're
any
straightforward because we build the scheme as like a completely modular system, so we don't need like any extra assumptions. We just need like, security of all the underlying primitives that we're using, but in a completely black box way.
So if I gave you a practical polynomial evaluation with small overhead,
Yeah, then maybe this would become,
so that's the main source of
Yeah,
why you say it's theoretical.
Yeah.
Okay.
Yeah. But I don't think that's an easy thing to do.
I think this algorithm played a role in some important PIR results recently too. So it seems to be useful in cryptography, maybe broadly, but seems totally impractical, or at least not good off.
This throws the gauntlet. Like we know it's possible in principle. Can you have a practical version of that? Interesting.
Yeah, I mean, when again, I didn't know about this result by Uman and forgetting the first author now. So when I saw it, I was actually pretty impressed that we can do that so efficiently.
Have you thought about the model where there's like a private encoding? So there's like the model where I encode the file and upload it, and then I want to audit that it's being stored later, which is usually much simpler. But I guess I haven't seen this idea of like constant size number of challenges. I don't know how that.
So if you have a private encoding, would that like compose well with this like blockchain consensus kind of thing?
Usually not. It's
Right.
usually used for other applications.
Right.
But I was just wondering because it's kind of like the two modes for proofs of replication. It's
Yeah.
like where you have public encoding and private encoding.
Yeah, I mean, we had the setting of like, consensus here. But yeah, this might be interesting as well.
I mean, yeah, it should be strictly easier because you can always use
Right.
the public encoding scheme,
Right.
but sometimes you can do much better.
All right, thank you.